Okay, good morning, everyone. So let's begin the real work from today. First things first, let me take some time to answer some questions. One of the first questions was about homework uploads, like the scan uploads, right? So homework as a category is worth up to 35% of your overall grade, 25% of which is devoted to online Pearson work, and 10% of which is the submission of the actual work that you do. So the assumption is that students will be working, let's say it's a problem, right? Whether the problem is small or big, doesn't matter, but you'll be working on something, right? Either it's some scratch work on some actual paper, whether it's on your writing tablet, doesn't matter what you choose. You would take a PDF of that work and you will upload it. And that is the homework PDF uploads. It also said scan homework uploads. Okay. And so that is like a credit, no credit category. If you upload it and it shows the work that you have done, you get full credit. If there's no submission, you get 0 credit. So as long as it's submitted, you own the full 10%. If it's a true or false question or a multiple choice question, simply write the problem number and write T/F or MC. You don't have to write out everything, okay? Because you're already submitting the answer. Is that clear to everyone? Okay. Any other questions? Feel free at this time. Okay. All right. So at this point, if anyone wants to leave, they're free to leave. We'll begin homework number 1. So homework number 1, homework 00 is simply tutorials. So if you have never used Pearson before, this is a great way to actually learn what the system is, how it works, how it functions. It requires specific entries of numbers. For the most part, it's pretty standard. Some things it's a little weird about. But if you ever need to refer back to it, then this is the place to actually go through, right? So homework 00 is just learning activities. There's no due date on it. There's no credit for it. There is a due date that shows up in the calendar, but it's always going to remain open. You can access it anytime. All right, homework 1, circuits, currents, and voltages. How many of you have signed up for mastering Pearson? Okay, I think I saw the roster, pretty much almost everyone was on there, so some students are still remaining. All right, so the first one is a tutorial. A tutorial is, in some homework assignments, tutorials go above and beyond what we are normally expected to cover in the syllabus. So that's for students who want to learn a little bit more, okay? So we will not be able to spend much time on it, if any at all, on those extra credit problems, okay? That is for students to learn on their own. So there are some video tutorials with guided tutorials. There are some actual problem tutorials. Those are all for extra credit. It's a little bit of extra work that takes you a little bit beyond. Some of them, not all of them, but it takes you a little bit beyond what the normal syllabus is expected, okay? So it's a little bit of extra work. That's the extra credit that you can earn if you wish to, all right? So that's tutorials. And it basically takes you, there's a learning goal, there's some theory about it, and then it works you through some problems and things. And then the actual problems are here. So the first homework is 1.5. If you have your laptops, let's get started. We'll spend some time on each question. If you have any questions, feel free to ask. Okay. So I should be in standard view, not in student view. I mean solution view, because it was already showing the answer. All right, let's see. Mastering engineering. And this is being recorded and it will be posted online. Okay. So question 1, choose the correct definition for electrical current. how do we define current? Right? We have a circuit, we have either a voltage source or a current source, and we have a potential difference at two ends of the source. And so it forces that potential difference, forces electrons to move. Now, when electrons move, the rate, so they are conducting charge. So charge is moving, energy is being transferred, and the rate of flow of this charge is defined as electrical current. And so the correct definition of electric current would be, anyone? Absolutely. Yeah. So for something like this is a multiple choice question. So on your work, you would simply write 1.5A, multiple choice MC. That's all you would do in your work. You won't have to write everything out. Move on to the next one. I'll just wait. Okay. And the answer to the other question is already in, sorry, not the answer. The unasked question is, of course, what is the unit for current? And the answer is already in there. That same statement that we pick up already has the answer. The unit for current is named after amperes, so it's called amperes. Or we use amps for short. So far, so good. All right. What is the definition of voltage? The first one or the second one? Yes, that's correct. So voltage is nothing but the difference in electric potential between any 2 points. Okay. If 2 points are the exact same potential, exact same electrical potential, the difference between them is 0. So the voltage between those 2 points would be 0. In ground terms, in reference terms, we say everything is reference to ground or earth because it actually, there's a return wire that actually goes into the ground, and we say that's 0 volts potential. So anything above that 0 volts potential, it'll have a voltage. So if we say that the surface of this table is 0 volts potential and point A is at, let's say, 5 volts above, then we say the voltage between those 2 points is 5 volts. Now, if we had 2 points, both of them at 5 volts, then the difference between those 2 points is equal to 0. So the voltage between those 2 points would be 0 volts. Even though measured with reference to ground, both points are at 5 volts, the difference between those two is exactly equal to 0 volts. So it is the difference in electric potential between any 2 points in a circuit. Okay. And if both points are the same potential, then it's 0. And unit for voltage is volts, named after a physicist named Volta. And as we go along, you would hear in all fields of engineering, all scientific fields for that matter, anytime a new discovery or research is conducted, chances are there are usually a lot of people behind behind the scenes, but the person who's in the front gets credited with that discovery, and it's named in their honor and named after that person. And so it's the same in electrical engineering. Many of the much of the work has been done by a lot of people, but there is a significant contribution from one single person, and they get to have their name on it. And so unit for current is amps, named after, or amperes, named after ampere. Unit for voltage is volts, named after Volta. All right, correct definition for an open switch. So let's bring up the notebook. Let me HW-01. Library. Okay. So any guesses? What's an open switch? So here's where we use a mechanical valve analogy. Okay. I'll explain what the analogy is, and then you can decide for the answer yourself. All right. So a mechanical valve is analogous to an electrical switch. Okay. But normally, when we talk about valves or switches, we say they're open or closed, right? So now this is a crude illustration of a pipe with a valve in it. All right, let's say this valve is just a flap valve. What do you say about the valve? Is it closed or open? It's closed, right? So a closed valve, does it permit or not permit any flow through it? Right, so it's blocking. So a closed valve does not permit flow. On the other hand, if you have an open valve, flow is permitted. Electrical switch, let's say this is a wire. This is the symbol for an electrical switch. Open switch, does it permit current to flow or not? Anyone? No current flow. Because electrons need a pathway to flow, If the circuit is open, there is no current flow. Voltage could be present, as we see in our power outlets. We have power outlets all around the wall in this room. We have power outlets running on top. All of those power outlets have voltage, but the circuit is open, so no current is flowing through. Not unless we plug something into the power outlet or a device or an appliance, there's no current flowing through. So in that sense, an electrical switch is completely opposite of a mechanical valve. A mechanical valve, when closed, does not permit any flow. An electrical switch, when open, electrical switch, when open, does not permit any current flow. And to actually have flow, we need to close the switch. So closed switch could be indicated like this. So in order for current to flow through, the switch must be closed. Let's take a pause. Let me know if you have any questions. So now let's get back to the question. The actual question was, choose the correct definition for a switch or for an open switch. So what do you all think is the answer? Yes. So one student says answer is B or 2. Anyone concur? I see some nods. Yes, it is. And as I said, right, open switch, no current flow. So we eliminate the other choices. Current through it is 0. And the voltage could be any value, similar to what I just said about the power outlets. Power outlet voltage is, anyone? I'll get back to that in just a minute. Anyway, so the voltage across it can be any value depending on the circuit. If you're running a DC circuit like 5 volts, let's say standard digital volts, 5 volts, be 5 volts, 15, 20, 100 volts, 500, 1000 volts, could be any number. So answer is B. All right, so coming back to that general knowledge question. What is the voltage of our power outlets? Yes, I heard something over here. Without looking it up. All of North America runs on 110 to 120 volts. Okay. Outside of North America, most parts of the world run on 220 or 240 volts. There is a reason for that. Late 1800s, and you can, of course, review this in the lecture videos. One of the earliest power stations that were set up were in the US. Electricity was a new thing. The only thing people knew about electricity until that point was lightning storms, which could actually kill people, very dangerous. So when they set up these power lines were also very dangerous because, of course, they didn't have any safety standards. So people were afraid of this new technology. And so as a way to alleviate technology, they said, okay, let's settle onto a nice round number, around 100, built up to 10% tolerance in it. So it went to 110. And then over the years, I think that 110 bumped up to a little to 120. Or that's the so-called history. But the rest of the world followed shortly after. They chose a higher voltage simply for the reason that electrical power is a product of voltage and current. P is equal to V times I. So if you want higher power to be delivered, you either increase the voltage or you increase the current. Well, if you increase the voltage, there are some pros and cons. If you increase the current, there are some pros and cons. But if you increase the voltage, it has more pros than by increasing the current. When you increase the current, it requires more expensive transformers, more expensive equipment, more expensive wiring, far thicker wires, plus it's more dangerous. So it is far better to increase the voltage in order to increase the power. And hence, most parts of the world run on 220 or 230 volts. If you look at your mobile chargers or your laptop adapters, it'll state every single appliance, every single consumer electronic device that you plug into a power outlet will have an input voltage and an input current rating. It's there. It's very tiny. My old eyes can't read it, but it's there. And it will tell you 100 volts dash 240 volts as input. So you can plug your chargers, your adapters anywhere in the world, and it will be electrically safe. You would not require an electrical conversion. You would require a physical adapter conversion, but not an electrical conversion. Okay, and output would still remain the same. Output would be like 5 volts or 15 volts or 19 volts, depending on what device you're using. So if you look at your appliances, it will say 120 volts as input. If you look at your consumer electronic devices, it will say you can use it anywhere in the world from 100 to 240 volts. All right, coming back to our homework question. Part D, choose the correct definition of a closed switch. This should be straightforward. We eliminate the first thing, which is if it's a closed switch, then it permits the flow of current. So the current cannot be zero, right? Unless, of course, the power is turned off. But technically speaking, if there is power, if there's voltage present, current would not be zero. So we eliminate those answers. And similar to the previous one, what do you think the answer is in here? Yes. The last one, right? Yep, that is correct. Circuit element that is used to control the flow of current. The voltage across it is zero. And we'll talk a little bit more about that in just a few seconds. The current through it could be any value depending on what the circuit is. So, if you're applying 5 volts in there, 5 volts, 1 amp, you could have 1 amp flowing through. Okay. Why is the voltage across it zero? Remember, you have 2 ends of the switch, right? 2 ends of the switch. Now, when the switch closes, both ends of the switch are now connected to each other. It's connected by a wire. And this is an important concept. When you have a circuit, let me bring up that illustration again. When you have a circuit like this, right? There's a branch of a circuit, switch is closed. Both ends of that switch can be considered to be individual and separate. But once the switch closes, they are now connected together. So any point in a circuit, let's say you have 2 points in a circuit. If they are connected together by a wire, then we are shorting those terminals out. It's known as a short circuit. Okay. I like to call it SC for short. So if you have 2 points in a circuit connected with a wire, they're essentially the exact same point. Doesn't make any difference. It's the exact same point. And if it's the exact same point, that means that the difference in electric potential between those 2 points is zero. So this is an important concept because when you're modifying circuits, which will come later down the line, we will place a short circuit and modify the circuit. And what that does is it will create a junction between those 2 different points. Once it creates a junction between the 2 points, the voltage difference between the 2 is equal to 0. So if one point is at 5 volts, both points would be at 5 volts, just as an example. So now current is flowing through the circuit, but there is no difference in potential between the 2 points. So the voltage across those 2 points is equal to 0. When we apply it through the switch, that means that current flows through the switch. The value of the current could be anything depending on the circuit, but the voltage across the 2 points of the circuit would be equal to 0. And this is an important concept. Okay. So the correct answer is, of course, E. But this concept is something that we'll use again and again the rest of the portion. All right. DC and AC. DC and AC. What do you think? Direct current and alternating current. So I will let you choose the answer later, but the explanation for that is this. Current and voltage are physical quantities. We can plot them as a function of time. So if you have time on the x-axis, typically we use seconds. And this could be voltage or current or power. If the value of this quantity is the same at any given point in time, then it's constant. Right? It's constant. Let's say this is voltage. And if you say this is 5 volts, it doesn't change its value, holds its value steady. So this is known as direct current. And any quantity that changes its value at any given point in time is known as alternating. The reason it's known as alternating is because when they first generated electricity, it would alternate. So it was a rotating alternator that rotated inside a magnetic field between the north and south poles of the magnetic field. And so it would alternate between a positive and a negative value. And hence the name of this kind of power was named as alternating current. Now, that current does not mean anything in this case. We simply refer to as DC and AC. Okay. And we use DC and AC for both voltage as well as current. We also use it for power. So all electrical quantities can be referred to as AC or DC. It sometimes gets weird because if we expand that acronym, and if we say it's DC current, we say direct current current or alternating current current. But I've never ever heard anybody say that. Okay, we simply use the acronym AC and DC. That's all. So this could be alternating. And then alternating could be any shape or any waveform. Could be square, could be rectangular, can be triangular, sawtooth, random noise signal. But the most common by far is what I've drawn here, some sinusoidal waveforms. This is something we'll learn in chapter 5, way down the line. Okay. And so those are the last 2 questions in that problem 1. Then, since this is the first time we're doing this, I'm going a little bit slow. But let's move on to the next question. In a fluid flow analogy for electric circuits, what is analogous to a conductor? I think we just spoke about that, didn't speak about it, but I used the analogy of the electrical switch versus the mechanical valve. So electrical switch was an electrical conductor, which allows conduction of electrons. What was the analogy that we used in there? Yep, Frictionless pipe, that's what it is in there. What is analogous to an open switch? I think we already covered that. Fluid flow analogy, what is analogous to a resistance? So resistance, electrical circuit, as the name suggests, it resists or opposes the flow of electrons. Hence, that physical quantity is known as resistance. And the physical device is known as a resistor. Now, all of this is something that you've obviously studied earlier. So hopefully you have the answer to that question. Fluid flow analogy, again, what is analogous to a battery? Anyone? Pump, absolutely. And that was the last one for this. VBA and VAB. I make this a little bit smaller. All right. Assuming you have watched the first few lecture videos. What is the value of VAB? Voltage V is given as 10, which is right here. Now, voltage has a difference in potential, right? Electrical potential difference is voltage. So we note the lower and higher end of this voltage by plus and minus signs. The lower end or the lower potential is noted with minus, higher with plus. When you have this kind of arrowhead, which typically I've never ever seen in electrical circuit where we use a single-ended arrow. Either it's a two-ended arrow with arrows pointing at both ends and plus minus signs are indicated, or it's simply a plus and minus without any arrows. I have never ever seen a circuit where you only have a single arrowhead. With a single arrowhead, what does it indicate? Anyone? Yes. Yes, that is correct. So the arrowhead indicates the plus, the tail end indicates minus. So here we are stating, or the problem is stating, that A is higher than B. A is higher than B, and that value is 10 volts. So then what is VAB? What is VAB? And then what is VBA? Yes. Absolutely correct. So when you have two subscript notation, the first subscript is the point of measurement. And the second one is the point of reference. So if you're measuring something, you always need a baseline, right? We always need a baseline. We are defining voltage as the difference in electric potential between any 2 points. So if you're measuring the voltage at any point, then we need a baseline. That baseline is known as a reference point. And so if it is VBA, we are stating we are measuring the voltage at B with a reference at A. So in this case, A is above B, right? A is above B. So my reference point, my baseline is at the top. I'm actually looking down at the point. And so B is 10 volts below A. Hence, VBA is minus 10. The difference does not change. The difference remains 10. That does not change. Okay. I'm like 5'5" or 5'5.5" barely. If I turn upside down, I'm just upside down, but my height still remains the same. So the difference between the 2 points does not change. All we are doing is we are changing our reference point. So VAB is 10, VBA is minus 10. That's all it means. And similarly, IBA is noted as minus 2. So IBA, if your current has two subscripts, then it indicates we are simply measuring the current that is flowing from B to A. That's all we are doing. We are measuring the current from B to A. And that is given to us as -2. So what direction is the current actually flowing? The opposite. The minus sign in any electrical quantity like voltage or current is simply for us humans. Okay, so that we are able to balance out our equations. So if a current says it's minus, all it means we are measuring in the opposite direction of the actual flow. That's all it means. So IBA means we are measuring current flowing from B to A is given to us as -2, which is the opposite of the actual current I that is flowing in there. So what is the value of I? Just the opposite, right? It's 2 amps. That's all it is. And now, here's the most important part, is the energy delivered to the element or taken from it. Again, this is part of chapter 1, the lecture videos. This is, again, an important concept. Okay. Remember, I said when you have a potential difference, when you have a source in the circuit that is supplying energy, that source supplies energy to the rest of the circuit, depending on the circuit components, whether you have a resistor or a capacitor or an inductor, a small chunk of that energy is dissipated as thermal energy, as heat. And the other part could be converted into mechanical energy. It could be converted into some other kind of energy. Okay. Some of it is lost as heat. So if you are a resistor and you're receiving the energy, or sorry, source is sending you the energy, then the resistor is receiving the energy. Mathematically, the way we define this is if we have a voltage, and let's go to the notebook. If you have an element, the element has two ends, and you say there's voltage across that element, plus minus. If current enters the negative terminal, as illustrated here, if current enters the negative terminal, then that element is supplying energy. Power is being delivered by the element. Okay. So current enters negative terminal. We say power is negative. Energy is actually element supplies energy. Okay. So if the current enters the negative terminal, power is negative. If current enters the positive terminal, power is positive. That's the simplest way to remember this. Okay. And mathematically, then you would use the equation P equals VI. If power is negative, you would use P equals minus VI. For the most part, if you are a source will always supply. Resistors, capacitors, inductors are all passive. They always receive. Okay. So if you go back to that question, what do we see? A is positive and I is flowing from A to B. So is I entering the positive terminal or is it entering the negative terminal? It's entering the positive terminal. So power is positive. If current enters the positive terminal, power is positive. Use the equation P equals VI. Now in the lecture notes and the slides, There are 3 examples that I've used. Even though power enters the positive terminal, we use P equals VI, does not mean that power will always end up positive. Depends on what we are provided with. These are just concepts. These are here, we are here to learn these concepts before we apply them to the circuits. One thing I'd like to mention in the few seconds we have left, all of these assignments in the first week and all of the theory that you're learning, this is something that is already covered in your prereqs, right? You've already learned about KCL, you've learned about KVL, Ohm's law, all of those you have done resistive circuit analysis, right? But as part of the syllabus, we are required to teach it again. So these are all based on your prereqs. You have already done all of this before. All of the concepts should be familiar to you. So this is a way to actually refresh your memory. The entire class of 201 is based only on 3 things. It's Ohm's law, KVL, and KCL. All other techniques that we learn are derived from these 3. That's it. If you can master these 3 techniques, you're good for this class. Because you'll need to be able to apply Ohm's law, KVL, and KCL quickly and efficiently. We will derive other techniques, but they're all based on these 3. These 3 are the only things that you need to know. That's it. Even electrical engineers, these are the only 3 things that you need to know. Right? Okay, so we did not get through the entire homework, but if you have any questions, feel free to reach out to me. There's homework. 1 is due either today or tomorrow, and then we have 2, 3, 4, 5, all in a sequence, right?